Thank you everyone for coming to this webinar, which is entitled Lighting Up the Future of Our SMEs. It is co-organized by Aerospace Valley and the CERFAX in partnership with ADOC and the EDIH Occitania. As you see, we have intervention from a lot of companies which will be introduced to you after during the roundtable. But first, we will start with a quick scientific introduction by Philippe Bouillet. So, Philippe, the floor is yours. Yes, you can go.
Yeah, thank you very much and welcome. It's a pleasure to introduce this webinar. And I will, maybe you can put the next slide, please, Quentin. Yes. So I will very briefly try to explain to you what we mean about quantum technology, what they are, and also what they are good for as an introduction to the various panels that you will be able to listen after my intervention. Maybe the next slide. So quantum technology is taking its essence in quantum physics. Quantum physics is a theory that is more than 1 century old, and that originated by the basic idea that the exchange of energy with any matter system or any system takes place in small quantities that we call quanta, like the photons of light or the different energy levels for other systems. And if you go to the next slide, and this theory has already a huge impact in our day-to-day life. By simply allowing us to understand what's happening at the infinitely small scale, for instance, what is happening in a conductor or a semiconductor, or how atoms are emitting light together, that leads on one hand to the transistor, which is at the heart of computers, or on the other hand, at laser, which is at the heart of many technologies like communication technology. We are able basically to develop tools, instruments, that are changing our life, like GPS for positioning, or light for listening to music, or to communicating much faster thanks to internet. The second quantum revolution, and this is my next slide, is going beyond just understanding what's happening to can you go to the next slide, please? So it's going beyond what just simply understanding what's happening at the infinitely small scale. It's actually our ability of today to address, to control, and to detect individual quantum systems and exploiting some of their the quantum weirdness or the weird phenomenon that actually are predicted by quantum mechanics. And there are basically 3 big categories of phenomena that we exploit in this second revolution of quantum technology. The first is called quantum superposition, and that's really the idea that a single individual quantum system can actually behave in 2 different ways at the same time, or be at 2 different positions at the same time, or be in 2 different states at the same time. And this, like the Schrödinger cat that you may know, who is dead and alive at the same time. This superposition can actually lead also to another weird behavior of matter, which can be either described like a particle, so that you classically describe with classical mechanics, a wave like water or light. And the next and the most maybe prominent aspect of the second revolution is the fact that if now you take more than 1 individual quantum systems, you can entangle them, which means that their properties are tightly connected to each other, even though the particles, once they have been connected, can be very far away to each other. And this, for example, led to the Nobel Prize of last year. So let's try to review now how these weird properties can actually lead to some applications that will be the core of the panels in the following of this webinar. Let me first introduce quantum sensing, which exploits the fact that all these properties I mentioned before, like superposition, entanglement, is very fragile. Any tiny effect from the environment can actually lead to the destruction of the quantum nature. This is why, for instance, we need to isolate our quantum system in a certain way, that the quantum computer, I'll come back on that, have to be in these big fridges. But we can also exploit the fact that we understand extremely well how the quantum system will actually change or evolve thanks to the environment. And this is how we can actually measure the environment using single quantum systems. Why is it so good? Because we understand everything. Because it's a single quantum system, it can be very sensitive to a tiny change. But it's also, we know exactly what's happening. And if you think about sensing, you want to be able to detect changes. That's what usually called precision or sensitivity. But you also want to be sure that what you are measuring is exactly what you are looking at. In that sense, you have some trueness or some accuracy in the way you measure. And the quantum advantage of these sensors that you will probably hear in the dedicated panel is the fact that you can at the same time be extremely sensitive, look at very tiny changes, but also know exactly where you are or how you are actually measuring it. In addition to it, lots of these quantum systems are basically sensing without being intrusive, and that also leads to a lot of intrinsic application to measure magnetic fields, acceleration, rotation, temperature, etc. Maybe you can go to the next slide. There are many different fields of applications that actually can benefit from this new technology of sensing. It goes from sensing the environment using, for example, atoms to measure gravity. You can look at what's happening inside a volcano or under your feet. You can use also some sensors using atoms or using diamonds to look at the magnetic field around your brain, and that is good for medical application or even to build some new ways of interfacing human capability with a machine. And you can also send it to space to measure gravity, to help for sensing all kind of electromagnetic fields and etc., or to look at the tiny effects in the semiconductor. So there are a large scale of applications that will be also reviewed during the dedicated panel sensing. The next application you can think of is really using the fact that if you go now with more than one single quantum particle and you connect them very strongly together using quantum physics, that's what we call quantum entanglement, then even if the particles are far apart from each other, if you change one, the other one will know that it has been changed. And not entering into details, this is a very nice way to actually transfer some information between two different points using this quantum entanglement, knowing that if someone is trying to spy you, it will change one system, and the other one on the other side of the communication channel will immediately know that someone has been spying you. And then, of course, you can start some mitigation strategies in order to get a secured communication channel again. This is the whole field of quantum communication, which is really using the basic laws of physics to devise a new type of communication that will be secured not by interestingly having encryption keys, but by having physical systems that tells you that you are secured. And there are, again, lots of applications, and it's on the next slide. It goes from trying to build some networks on the ground between, for example, two banks to be able to communicate between the banks with a quantum secured network, exchanging quantum secured keys for encryption, that we call the quantum key distribution. But it also extends to much larger scale in which you need to go to space, for instance, in order to use either a satellite as a relay between two ground stations, or even think of a future quantum internet using an array of quantum based communication satellites that will actually allow us to connect two different sites or two different computers with a secured data channel. And finally, the last range of application, which is maybe the one we hear most about, which is probably the most promising, but also the most challenging, is a new realm of computing, which we call quantum computer. I mentioned before that already quantum mechanics allowed us to understand how transistors work and semiconductors work, and that led to making a computer. And these computers are based on data that is a series of bits, and a bit can take a value 0 and 1, and you encode all the information into this series of 0 and 1. If you go to the next slide, if you now think about quantum mechanics, because you can have quantum superposition, your bit will be a qubit, and this qubit can be in a superposition of 0 and 1. It can take any value, and any value means it can be a certain weight of 0, a certain weight in 1, and there is also a phase related to the rate between 0 and 1. This is why you cannot simply describe a qubit by just an arrow, but now it has to be a vector that can take any position in a sphere that in our jargon of scientists we call a Bloch sphere. And the operation of the bit now gives you an infinite amount of possibilities, much more than just a 0 or 1. And this is all this possibility that you can actually exploit in order to get much faster and much more efficient calculation. Of course, at the end, you need to retrieve the information, and the way you do it is you project your qubit into something that you can actually measure, which is, of course, 0 or 1. But the fact that all the computing can be done before you actually get this information at the end gives you a large realm of possibilities of parallelization of the calculation that actually is very promising for the future, and you will hear more into the dedicated panel of quantum computing. Just to finish about this, and this is my next slide, of course, this qubit is at the core of the quantum computing, and as of today, you can have different type of technologies. There are many different technologies for superconducting qubits, where you devise some circuits in which some tiny loops, for example, of current, will behave in a quantum superposition, creating a qubits if the current goes left or right, for instance. And this has to be protected for the environment in a very big fridge, and this is the typical picture you see in the background here, this big dilution fridge, where the system operates at a temperature of a few millikelvin. But you can also think of single quantum systems like atoms or ions, and you can arrange them, you can control the position of these bits or these qubits, atomic qubits, like you see on the picture. And this is this is at the heart of quantum processors, for example, of the company Pascal, who will be in the panel of quantum computing. And you can actually use entanglement, and you can use connection between these qubits to get this largely parallel possibility of calculating using qubits and really getting a quantum advantage in computing. So this is it for my conclusion, and this leads to my last slide. So this was really a general overview of quantum technology. I hope it gives you an oversight of what you will have in the 3 different panels. The next one will be dedicated on quantum computing, going deeper into the things I really very briefly introduced in this introduction. And then looking also at what type of quantum sensing can actually be really developed, where is the state of the art today, and finally about the prospect of using quantum communication. And thank you very much, and I leave the floor to the first panel then.
So much, Philippe. So as you said, the first roundtable will be on quantum computing. So I will leave the floor to Jean-Christophe Bureau, but first, if you have any question, you can ask them with the question panel on the GoToWebinar tool. So just ask them, and they will be answered at the end of each roundtable. So if you have questions on the first roundtable on quantum computing, you can ask them, and the animators and the people speaking will be answering them at the end of the 20-minute roundtable. So, Jean-Christophe, I leave the floor to you.
Okay. Before we begin the roundtable discussion, I'd like to bring to your attention that this webinar is organized in partnership with the European project Occitania. This project aims to accelerate the digitalization of companies. More exactly, we support all SMEs in their digital transformation project to become more efficient and competitive in the HPC field in particular. So please do not hesitate to contact the organizers for further information, FACS or Aerospace Valley. For the first roundtable in quantum computing, we are pleased to welcome Olivier from Eviden, Christian Beugnot from Pascal, and Charles Pro from Soprasteria. Just to start, first main question, what are the different technologies in the field of quantum computing? And what are the programming models? Who wants to start?
I can take the question if you want, Jean-Christophe. Just as Philippe said, I mean, the building block of a quantum computer is a qubit. And the qubit will be this building block which exhibits the 2 quantum effects known as superposition and entanglement. And today, I mean, if you see the global ecosystem, it exists, let's say, 6, 7 main technology to build this qubit. It can be atoms, it can be ions, it can be, in some cases, a spin of atoms or electrons. It can be also photons. And the question, I guess something we'll discuss in the near future, is when developing an application mean how your application will be, I would say, connected to a given environment. And in particular, I mean, dependent technology, I was just recalling the gate set, I mean, the gate available for each technology, or the topology, I mean, how the different qubits are connected is highly dependent of this technology. And one key question today is, when developing an application, how to develop this application without being too close, I would say, to the very basic hardware level, and in particular, giving a kind of overview of what kind of libraries, tools, compilers we could use at the end to be able to address, I mean, different application domain without taking into account too much, I would say, the hardware level. And last point, also, I mean, I just summarized, I mean, the different qubit technology exist. Also, keep in mind that it exists also three main, I would say, programming model. I mean, the way of, I mean, having the different qubits working together. And today, usually, we define, I mean, three main environments. One is called gate-based, meaning for this gate-based, you will have to develop, to apply, sorry, for each qubit a given gate, and you will build a circuit like that. Or also a solution, and Pascal is one example of what we call analog or annealing system. In this case, the system will, you will provide to the system a kind of Hamiltonian, and the system will evolve depending a certain environment. And again, and depending on the technology, the way you will develop an application will be very different. And I guess this is something we'll address and discuss in the near minutes.
Okay, thank you, Olivier. Christian or Charles, you want to add something? No? So
No, that's perfect.
Okay. So second question, when will it be operational? What will be the gain in computing speed compared to conventional HPC?
Yes, well, it also depends on what we mean by operational. So quantum computing is reaching a level of maturity where we can already see first use cases, first applications that are starting to reach a maturity in which they can have an impact on industrial scale problems. For instance, when we are talking about how to evaluate quantum algorithms or quantum methods, there has been a famous Q-score metric introduced by Eviden, who is an application-based score, which is actually the right approach to go about evaluating quantum methods. Since as it has been illustrated, there are many different technologies, and currently the development happens very, very close to the actual hardware level. So we need to keep in mind what hardware we are developing on, what type of machine we are developing on. And because of that, and because of the heterogeneity of the technology, being able to compare and evaluate these systems can be quite challenging. On top of that, what we can expect from in terms of gains is not necessarily an acceleration, although for certain types of use cases, especially in optimization and machine learning, we can already hope for a gain in terms of speed. But typically, we are more looking at gain in terms of precision, so gain in terms of accuracy, especially for complex computational task, which is more a short-term gain. And we also cannot forget that there is also the new metric of energy efficiency. So indeed, quite a few of the quantum technologies, if not all of them, can provide a comparative advantage compared to traditional, conventional, high-performance computing environments in terms of energy consumption, in terms of carbon footprint. So this is a metric that someone needs to keep in mind when they are trying to evaluate what is the added benefit of a quantum method or even a hybrid method.
Okay. And can we transpose classical algorithms? I mean, from HPC. that you were used to this?
I would say, unfortunately, no. And this is one key discussion. I mean, today, there is no, I would say, portability between classical and quantum computing, meaning that, let's say, you have an application running CFD or quantum chemistry on a classical HPC. You cannot take this application, put it, I would say, on the quantum computing computer, whatever technology, and expect a benefit. This will simply not work. And besides, I mean, the evolution and the maturity of the hardware level, a key challenge in quantum computing is developing application. I mean, what kind of use case in different industry, life science, banking, insurance, aerospace, quantum chemistry, what are the applications that will be eligible to quantum computing, and how to reformulate this application to a given environment. And this is, again, something I would like to highlight. I mean, on top of maturing the hardware technology, a key challenge is developing, assessing use cases and developing use cases.
Okay, so I will not be able to use my CFD schemes as usual, you mean?
Not today, at least, not today.
Okay. And what are the main domains of application? Maybe Charles or?
Charles, you're muted. Charles?
You are muted, Charles.
You're muted, Charles.
Open your microphone, please.
Technical problem.
Yes.
I think you can try to join on the phone, and Jean-Christophe will just ask the next question during this time.
So,
But you can try to connect.
While we are waiting for Charles, I can answer the question already, or
Yes.
at least partially, if that's okay.
Yes.
Yeah. So in terms of what kind of applications we are looking at, when we talk about potential utility for quantum computing, we typically distinguish three main domains, being optimization, typically combinatorial optimization problems, simulation, chemical or material simulation, or synergies with machine learning. So on the short term, what we expect is especially rise in terms of hybrid applications, so applications that rely on quantum technologies as well as classical resources, intelligently separated, divided, and deployed in order to make the most out of both worlds, I would say, for combinatorial optimization problems that manifest in any kind of scheduling or planning problem. The logistics industry, for instance, can expect some interesting incomes out of that. Another interesting aspect is going to be, and potentially the main impacted field is any kind of simulation-related tasks. So material simulation is going to be a huge thing, as it is impacting a lot of the manufacturing industries. And quantum computers have, I would say, a more natural language and setting to describe, especially on the microscopic level, how certain types of materials behave or react or should react. So designing new types of composites or material, we can expect some very interesting applications on that field. And a last example with the synergies with machine learning, what we can expect already in the short term is that reinforcing existing machine learning methodologies, be it neural network or kernel-based methods, can help out with a quantum layer to increase the expressibility of the data to increase the quality of the information we can extract from our data sets. So especially for more complex data sets or data sets that are coming from quantum sensing. So quantum sensor-based data sets can be a very, very interesting type of application that we should be looking at. Charles, did you manage to fix the microphone?
I don't know, do you hear me?
Yes, good.
Yes, we hear you.
Yeah, that's better, so sorry. So thanks to the mobile phone, I can participate to that meeting. From an IT services company standpoint, we have two main usage of the quantum computing. First is for simulation, and this is very, very important for every company that have an R&D activity. And secondly, for optimization, so every company that needs to optimize their operations. So in a nutshell, the quantum computing is eligible for all the sectors, all the companies, as far they have R&D and or a large operation to run. So that's would say the first step. After, there is a question mark about why investing now in the quantum computing, because as said by Olivier and Christian, we have not yet, we expect, but we have not yet an operational quantum computer efficient enough to run larger calculation. But four things to get in mind. First, the learning curve is years long. Secondly, industrial cycles are long, years long too. So that's really important if you want to onboard the quantum computing in a new generation of car, a new generation of planes. You need to invest by now. Third, it may be faster than expected. So that's something which is really, really important, because we have seen that with generative AI. Even Google has need months, more than 1 year, to be at the level of ChatGPT, typically. And fourth, it could be a matter to love or die, depending on your business, and if you not are well prepared on leveraging the quantum computing. So based on that, any company that should explore the quantum computing, not for everything, for specific subjects, specific matters for which it is really critical for their future. And after you have, depending on your activities, that could be a simulation, that could be optimization, that could be both. One thing that could be funny for everyone, that a lot of people are saying that we have to find the use case. But we, in the reality, we never invent a brand new use case. The problem of simulation and the problem of optimization are already there. So we are already tackling them with traditional computing, and the expectation is to go beyond, to go further, and to get a better resolution, better answer to the concrete industrial problem of the different clients.
Yeah.
Okay.
Yeah. And maybe one comment coming back to your point, Jean-Christophe. I mean, the maturity, I think, will also depend on the domain. I mean, we were talking about logistic, computer optimization. I think this domain will be, I would say, addressable, I would say, short term, not mid-term. However, we discuss CFD, if you discuss climate or some domain, the maturity is pretty far from there. So meaning that some domain that shall explain will be more mature than some other, and for this we need to wait, sorry, for the ideal quantum computer to be available to be able to address, for example, CFD.
Okay, thank you, Olivier, Charles, and Christian. And maybe a last question. What is the quantum computing ecosystem? Do you want to respond? Maybe...
Yeah. I could start, and my colleagues will complete. Compulsory, the first stakeholder is final clients. They need. We have to solve something. So this is we say at the center of our ecosystem are our clients. After we have computer makers. So we have honored today to have Pascal with us, and there are others. We have also traditionally software editors, and I think that this is, I would say, the starting point. But we also need the support of the academics to train the people to do deep research that must be done in advance, in the early stage of the development.
I do agree. And in fact, in particular, with a very active ecosystem with startups, with large companies, with a very active academic environment in Paris, Grenoble, and Toulouse also, of course. And this is how to move and to develop again the technology, but also working on the use cases and all the software stack needed for addressing quantum computing. And I think we are lucky in France to have this ecosystem.
And if I may highlight one more thing, is the key is that which is I find very, very nice about the current quantum ecosystem is partnerships. Partnerships that are happening on various levels and between various different actors, from hardware providers to software developer to numerical service providers, all the way to end users, partnering up to discover use cases, to develop methodologies, to benchmark, and even on the hardware provider side, I wanted to highlight a very recently announced collaboration between IBM and Pascal. So two hardware providers from very different technologies who are joining forces to develop new standards for quantum-centric supercomputers. So this has been announced a couple of weeks ago, and we expect some very interesting outcomes, especially in the HPC field as a whole in terms of quantum computing.
Okay. Maybe, Corentin, we can take a question from the audience.
So thanks to the four of you. So we have one question, which is, have there been any advances on the developments of quantum RAM, which seems to be a missing component to advance in quantum machine learning today? So if any one of you wants to answer this.
It's a very key topic, and some progress has been made over the last, I would say, months and years. Just to mention, in France, we're mentioning in the ecosystem, we have a company called WeLink, which is a startup working on this kind of development. And for sure, it is again not mature today to have QRAM available. However, it's a key roadmap and journey for quantum computing. And again, WeLink is actively working on this in France.
So thank you, Olivier.
Corentin, your microphone is off.
One more question. You can make them. You can have it. You have some time for one more question. If not, we can go to the next roundtable as you want.
Okay, one more question, maybe.
One of you, because the only question on the quantum computing was about quantum RAM.
Okay, just a last question for me. Have you project at European level, or are you involved in European projects, or is it just French cooperation? I don't know.
I mean, from our side, you know, we as Evident, we are deeply involved in many European projects. In particular, I mean, a few words on hybrid, I mean, mixing HPC and quantum, and we have different projects. And in particular, in Germany, for example, we have one project, this, and also working on silicon spin qubit, which are two main projects in which Evident is deeply involved. I guess Pascal and Sopra are involved in such projects too.
Yes, correct. So the Euro-HPC joint undertaking flagship project has a dedicated quantum site that is tasked to install various different quantum technologies in selected European high-performance computing centers. And it is currently reaching its second wave of procurement. So we can expect many more different technologies becoming available through these HPC sites. And Pascal is naturally participating in this initiative.
One last question, if you can answer it quickly, which is, how difficult will it be to mix quantum computing and HPC?
Charles, you want to address point, or you mean hybrid HPC? The question was hybrid and HPC and quantum. Sorry.
Yes, it was. How difficult will it be to mix quantum computing and HPC?
Here again, it's a key topic in which different actors are involved, in particular Pascal and Evident in Gensi. As you may know, there's a solution, a project called HQI in France, where the main idea is to see how to integrate, I would say, HPC and a quantum computer, a QPU, and this is something pretty difficult in which many activities are ongoing at this point. Programming model and how an application will take benefit of the HPC side and also, of course, on the quantum computing side.
In addition, we do not envision quantum computing for big data or large database exploration. So there is a lot of use cases where we need to decompose the problem in different sub-problems, and some of them will be tackled by the quantum computing, and others will be tackled with the traditional computing. So we definitely envision an ecosystem where we will have a hybridization of standard and quantum computing.
Okay, so I want to thank again Olivier, Christian, and Charles for this discussion, and we can move on the next roundtable, Corentin.
So thanks to the four of you. So the next roundtable will be on quantum sensors. So Olivier, you can stay here and introduce the participants.
Bye-bye.
So, well, okay, thank you. So I changed hats. I'm moving from quantum computing to quantum sensing. So before moving deep diving in the topics, maybe we could give a quick intro of each of you. So Jasper, if you want to introduce yourself and your activity at Airbus.
Yeah, thank you, Olivier. I hope you can hear me. So yeah, my role at Airbus is the central coordination of all of our quantum activities. So what we do in sensing, which is actually really important for the aerospace sector, but also what we do for computing and for communication. So you probably know Airbus from commercial aircraft best, but Airbus is actually more than that. We are also the largest helicopter manufacturer in the world. We are offering a variety of defense products, for example, military aircraft. We have also division for space products. And the beauty about quantum is that the whole aerospace sector is most likely going to be affected and impacted. So we can expect that our future products and services will strongly benefit from quantum technologies.
Thank you, Jasper. Sylvain?
Hello, my name is Sylvain Schwartz. So I'm the director of the Quantum Lab at ONERA. So ONERA is a French public institution devoted to doing applied research in the field of aerospace. And so in this lab, we're studying quantum technologies with applications to the aerospace industry along 5 pillars or axes. So quantum algorithms for quantum computing, as was discussed earlier, quantum communications, quantum optronics, quantum sensing, especially with cold atoms. We have inertial sensors and electromagnetic field sensors with cold atoms, and quantum materials for single photons applications.
Thank you, Sylvain. And now, Matthias?
Yes, thanks a lot for giving me this possibility to participate to this webinar. So I'm Matthias van den Bosch, not Corentin Pratmarca, as is written at the bottom. So I work with Thales. I work in the space division of Thales, which is Thales Alenia Space, where I am responsible for the preparation of the future in general, all technologies, but in particular with a close look at quantum technologies. So, you know, as a company, Thales is known for its involvement in both secured communications and sensing, and basically the way to gather information on sensitive topics so as to be able to make the right decisions at the right moment. And so the idea behind all that is that we are involved in all these very upstream technologies, because our shareholder, which is the French state, requires us to be able to master this kind of breakthrough technologies so as to be able to build the critical systems of the future that our, different governments, France and Europe, might need in the future. And so we are very much involved, and this has been the case for the past 25 or 30 years in quantum sensing. And we have also had strong contributions to quantum communications. Actually, we have patents in quantum communications that have fallen in the public domain because they were already 20 years old. So that gives you an idea of the involvement of the company.
Thank you, Matthias. So, for those who are not experts, could you just summarize what is quantum sensing and what are the technology behind quantum sensing? I don't know if Matthias, you wanted to take this first question.
Yes, I can take this one. Okay, so basically, as Philippe Bouillet said in the introduction, quantum technologies use very, individual quantum systems. And these quantum systems are extremely fragile objects. They are extremely sensitive to the environment in which they lie. This makes them a very interesting probe and a very efficient probe to gather information about the environment in which they are. So now, this is the general idea. And now there are 2 main branches of quantum sensing. There is one branch that is related to, let's say, sensing space and time. And there is another branch which is related to sensing the electromagnetic field. That is the two physical fields, 2 physical quantities that have some sort of long distance propagation, and so can be detected without being right on the spot. So if you talk about space and time, the first example is atomic clocks. An atomic clocks is very mature in the sense that there have been atomic clocks working as quantum sensors since probably 4 or 5 decades already. The GPS and Galileo have atomic clocks at their heart. So you see, it's extremely mature, but there are also much less mature, much more advanced development in atomic clocks. Another way of sensing space-time is to measure acceleration, for instance. And accelerations mean, of course, acceleration just when you are in your car and getting faster, but also means rotation, because you can feel a rotation in centrifugal forces. And it also means gravitation, because gravitation is just another acceleration, and Philippe Bouillet knows that very well. And so the idea is that you can sense space and time, at least using those two things, and actually even gravitation fields, gravitation sensors can become time sensors at some point. This is the first side. The other side is electromagnetic sensing. And again, with electromagnetic sensing, what you can do is you can sense very, very accurately and very, very sensitively electric field, that is radio waves and light, and magnetic field. And the idea behind that is that you using atoms, and in different kind of setups, you have different ways of sensing a magnetic field and electric field. I mean, Sylvain is one expert of that. You have the opportunity to have extremely sensitive sensors with a tiny size. For instance, you can have a radio antenna, which is the size of a thumbnail, which is actually as sensitive as an antenna that is several tens of square meters. And so this is extremely interesting. And this relies on either playing with just single atoms or single groups of electrons in some crystals. And the other option is to use superconducting setups, where you have actually the possibility to sense the magnetic field at a very, very tiny scale. So you see very broad range of different technologies.
Okay, thank you. That's very clear. One maybe very naive question: what are the quantum advantage and quantum advantage? Sorry, we could expect from quantum sensing. I mean, compared to classical way. I mean, what are the expectations from quantum computing to sensing? Sylvain or Jasper? Sylvain, yeah.
Yeah, okay, I'll take that one. Yeah, so as Matthias and Philippe said before, of course, the first quantum advantage one can think about is sensitivity. Those small objects can be made very sensitive to the thing they are sensing. For example, a Rydberg atom, to measure the electromagnetic field, is very sensitive because a Rydberg state is a state where the electron is very far away from the nucleus, so that makes a huge dipole, and that makes such atoms extremely sensitive to the field. That's one example. Another one would be an atomic gyroscope. If you want to measure Sagnac effect with a matter wave instead of an optical wave, then you also gain a factor like 11 orders of magnitude on the sensitivity on the Sagnac effect, just because you are using different waves, and they are intrinsically more sensitive. But it should be kept in mind that it's not the only advantage you could gain from a quantum sensor. Another one which is very important is the fact that such sensors can, in some circumstances, provide absolute measurements. So here I would like to quote the gravimeter, for example. If you would like to measure gravity or acceleration with a classical sensor, basically you would measure forces that are exerted by your accelerations, inertial forces, on a mass, and you will like a mass which would be attached by some spring, and you would look at how the spring deforms in the presence of the inertial sensors, in the presence of the inertial forces. Sorry, that would be a classical inertial sensor, and this one you would need to calibrate it. You would measure what is the length of the spring in the absence of forces, and then of course, if the temperature changes, or if your spring ages over time, that would induce drifts. And so those sensors, you need to calibrate them. They are called relative sensor. And conversely, a quantum sensor, or at least some of them, are absolute sensor, in the sense that, for example, if you want to measure gravity with atoms, you're going to look at how the atoms fall, like in vacuum, also in conditions where they are very, very little disturbed. you manipulate them with lasers, which are also stabilized on atomic references. And so such a sensor, you don't need to calibrate it. It provides an absolute measurement, which is directly related to the properties of the atoms themselves. This is also true for an atomic clock, which also use as the fact that all the atoms are, all rubidium atoms or cesium atoms are the same wherever and whenever you consider them. They are all identical, and that provides the etalon, if you want, to calibrate this sensor. So sensitivity, absolute measurements, and again, these two are not the only ones. As Matthias said, you could also, for example, in some circumstances, get a quantum advantage in terms of size. If you want to measure a radio a frequency wave, which has a wavelength, I don't know, of 1 meter or 2 meters, then you would need, if you want to do that with an antenna, you would need a very big, tall antenna. Those exist. But of course, if you do that with a quantum sensor, you could reach the same sensitivity with a much smaller size. So here's the quantum advantage would be size. Or one last example would be an NV sensor to measure magnetic field in a very sensitive way. So those NV centers, you can place them in very, very small, like nano diamonds or at the end of a diamond tip. And then you could move that with a very, very good spatial accuracy. So here you could, for example, measure the magnetic field at the surface of some material with a spatial resolution, which is at the nanometer scale. And so here you exploit the fact that your probe is just a tiny quantum object, which can then measure the magnetic field with a very good spatial resolution. So that's yet another example of a quantum advantage.
That's very clear. Thank you. Thank you, Sylvain. Just one question on the maturity and the technical challenge, where we are on this journey of developing quantum sensing, Jasper.
Yeah, I take this one now. So I think if you look globally at quantum sensing and you compare it to other quantum technologies, in particular quantum computing, it's fair to say it's a quite advanced stage compared to other solutions. But of course, the situation is not black and white. We have some particular technologies which are, I would say, on a subsystem level quite far developed. Prototypes are existing. There's a commercialization is ongoing. And I think we can expect that also for some other technologies, this will continue in the next years, just because there's so much efforts coming from the community and also a lot of investment coming. So I think overall, these are I think very good signs. The question is now, can you just take a quantum sensor if you have, let's say, solved this and you have the first prototype as a commercial product, and does it already provide a value directly? And this, of course, is then also something which is difficult, because you need to integrate these sensors into real life applications. And now I'm speaking from the aerospace sector, where this is in particular a challenge. So for example, we are in the system integration, we are quite often for our sensing, for example, in navigation, this has been brought up already, we are fusing classical navigation systems with quantum enhanced sensing, which means there's a lot of challenges on the operational level. And for example, Airbus is conducting a variety of test flights to understand how do we in the best way integrate these sensors and how do we fuse this information and what is the end-to-end performance. So on the system integration level, there is challenges, of course. Next step is then, this is also in particular relevant for the aerospace sector, is certification. So once you have a system which provides a value, and you have proven that on, let's say, an R&T level, you have to make sure that this is certified by the authorities. So, and this is also a longer process, which we have to take into account when we talk about, let's say, challenges. And this is something we have to anticipate very early. So we have to iterate early with the authorities and also with the manufacturers of the subsystems to make sure that this is a process which goes as smooth as possible, because this is absolutely necessary to get the full certification of such systems. And so far, quantum is a new technology, so of course there will be some questions and some proofs we have to provide. And then the third thing, which is also very important from a commercial perspective, so to have a sensor which has a better performance, or we have already heard has better swap, has for example a low drift, is great, is very important and can provide an important value. But there are many other things on the commercial side you have to consider. You need a redundant or a reliable supply chain. Otherwise, it's very risky to integrate this into a product. You have to make sure that the costs are acceptable. You have to make sure that the system you integrate into your product is robust in the sense that the maintenance costs are kind of under control. So, and this is also a very important question. This is something which is maybe today not really clear, because we don't have, let's say, these broadly integrated systems. So there are some unknowns. So bottom line is, it's still a way, I think, to go and to bring these great technology from enhanced capabilities into value, into final products, commercial value, societal value. And I mean, to make this happen, what's really important is, and this is what we are also doing with many companies, is to collaborate. I mean, in the end, you have to bring the component, the subsystem manufacturer with system level manufacturer together in order to make that happen.
Okay, thank you. Thank you, Jasper. Yeah, I think the time is flying, but at the end, we discussed on the technical side from the quantum sensing. Now, I would like to say a few words on the application domain. So, in your different, I would say, domain or industry, what is the main application you see, you foresee for quantum sensing in your domain? I don't know if who wants to start. I mean. Also, I know that depending the different technology existing, I mean, are you using at Airbus, Onera, and Thales the same technology? And yes, and what for? What are the applications you are looking for?
Maybe I can just compliment, because I just
Sure.
brought up the example of navigation. So maybe, I mean, navigation is obviously for aerospace a core topic. It's for aircraft, helicopters, it's for all of our vehicles basically. And also today, when we build our aircraft, we're using from suppliers navigation systems. So this is already an established setup what we have, and this is one of the technologies we are pushing at the moment. We have done many hours of test flights. We have made many lessons learned. We have focused here on a diamond-based quantum sensor, so an NV center based to measure magnetometry and to use a technology, which is a technique which is called map matching. So basically, you compare a measured magnetic value with an anomaly map, and this brings you the absolute calibration of your navigation system. But there are other ways. Quantum inertial forces, Sylvain was mentioning this, and maybe he comes to that later on. There's another project, another technology and exciting opportunity, I think, where we are strongly engaged at the moment. This is to bring quantum sensors and its capabilities into space. So Airbus is very engaged in satellites, also in Earth observation satellites. They are using today already very sophisticated sensors, classical sensors, and quantum sensing is naturally like a super interesting option to improve this capability. And we have one project where we're also collaborating with many partners in the ecosystem. It's called Carioca. It's a project where we aim to bring an ultra-cold atom-based inertial sensor into orbit. It's going to be a prototype, but this prototype shall verify that this technology works in space. And once we have this in space, we can use that to improve significantly the way how we measure the gravity field of the Earth. And also here, I think Sylvain was already mentioning, we are not talking about a factor of 20%. We are talking here about a significant improvement, in particular in terms of the drifts. And once you get rid of these drifts, you can measure data in the future which are more accurate, hopefully significantly more accurate. And these data will, for example, serve scientists who do climate modeling to improve their modeling of climate change. So this is really like an added value which quantum sensing can provide. And Airbus is very proud to be here. We are the system integrator for for this project. So what we often do, so we bring different subsystems together to develop the satellite. And this is going to be a very, very novel way of doing sensing from space.
If I may catch the ball here, so Onera is also part of this Carioca project, and we've been working on this hybridization between classical accelerometers and cold atom accelerometers for a few years from now. And yes, the idea here is that those classical accelerometers that are already present on board satellites to measure the Earth's gravity field are already quite good, extremely sensitive, but there in the longer term there are drifts, and that's where the cold atoms accelerometer, as Jasper said, could bring an added value. Again, here's the quantum advantage is to, as I said before, to reference your measurement to the atomic properties themselves, which do not drift. And so there is a hope that those cold atoms accelerometers could nicely complement those classical accelerometers in the low frequency domain or the longer term domain to compensate for the drifts. Yes.
Okay. Thank you.
Okay, and so since Jasper and Sylvain have talked a lot about space-time sensors like accelerometers, I would like to give a little bit more highlight on the magnetic side. Also Thales will also develop a quantum inertial measurement unit. But okay, I would like to take this electromagnetic side from the system point of view also, because it's also, of course, it's very important to know why we are doing the thing. So there are different systems in which this kind of electromagnetic quantum sensors could be used. That can be, of course, in space. Like, you can be very interested by knowing what is going on in terms of spectrum around the Earth, especially in these days where electromagnetic field is used by hostile entities. But you could also be very interested in using electromagnetic sensing so as to know better the environment of the Earth, again in space, so as to be able to predict, for instance, the impact of a solar storm on the ground infrastructure, like on telecom network or on the power distribution network, and these kind of things. And there are also non-space applications. For instance, if you are able to measure with a tiny diamond, as Sylvain was mentioning, and measure the magnetic field at a very accurate location, actually, you can think of this kind of uses in medicine. For instance, if you want to be able to measure the electric activity of a neuron in the neural system, then it can be also very interesting to be able to master this kind of technology at this level of accuracy. So you see, there are a number of potential use cases of electromagnetic sensors based on quantum physics that could be reliable.
Many thanks, Matthias. Corentin, I know I'm lost with the timing. Could we have time for a few questions, if any?
No, it's been 20 minutes, so it's the end of this roundtable. If you want to say something for the end, Olivier?
No, just to thank mainly the three speakers, Matthias, Jasper, and Sylvain.
Thank you.
Thank you.
Pleasure.
So thanks for you. So the next roundtable will be on quantum communication. I will let Anaïs Dreo introduce herself and the two speakers.
Okay, thank you, Corentin. So you hear me well? Okay. So good morning. My name is Anaïs Dreo, and I'm a senior researcher working at Laboratoire Charles Coulomb with a joint lab between CNRS and University of Montpellier. And we're also part of the Institut Quantique Occitan, which gathers all the academic labs and private companies working on quantum technologies in the Occitanie region. So here, I'm pleased to chair this roundtable about quantum communications, and we're going to welcome our two guests that have already been introduced previously in the quantum sensing session. So Jasper Simon Crowther, who is the central coordinator of quantum technologies in Airbus, and Matthias van den Bosch, who is the director of research, technology and products, and in charge of the quantum technology roadmap in Thales Alenia Space. So before starting the discussion, I think it would be interesting to give a brief introduction on quantum communications for the people who are not that aware of this field. So the goal of quantum communications is to exchange and distribute information in a secure way over distances using quantum light. And so one way to do that is to use single particles of light that are called photons. And to give you an idea, if you use a standard 1 milliwatt laser pointer that you use for PowerPoint presentation, so during 1 second, you have the emission of on the order of like 3 millions of billions of photons. So in quantum communication, the idea is to directly use each of those photons to encode the information on their quantum states. Their state could be, for instance, quantum superposition or entanglement, as you heard before. And here, switching to quantum communication, and I want to emphasize this point, is not at all an upgrade of equipment. You don't need to like just purchase more sensitive light detectors. It's really a new, it requires really change of technologies and protocols, and also like mindset and trainings of people. So why I want to go there? So as it's been said by Philippe Bouillet, the idea of quantum communication is that it can provide you with inherently secure communication, provided that we perfectly control and detect our quantum systems. And why? That is really linked to a fundamental law of quantum mechanics, the fact that you cannot clone an unknown system, and whenever you're going to want to measure a quantum system, you're going to introduce perturbation. So in practice, if you have a quantum channel, and when you want to spy on it, you will introduce perturbation that can be detected. So quantum communication has been investigated for more than 2 decades in academia. So there's a lot of pioneering proof of principle experiments. And so here I want to, since we're in a webinar co-organized by Aerospace Valley, I want to emphasize the very impressive results that have been achieved by the group of PANs in Hefei, China. So 7 years ago, they were able to establish a quantum link between 2 ground stations through a satellite, and the 2 ground stations were separated by more than 1,000 kilometers. So this is already very impressive, but the next step, that is the goal of going to scalable system and real-life implementation, is an extra challenge. So to discuss about that, first I will ask, so Matthias, in your company, in Airbus, so sorry, in Thales Alenia Space, why did you get interested in quantum communication?
Okay, thank you. So we've been interested for 2 reasons into quantum communication. The first one is that, as I said before, we have the mission by our owner to develop this kind of technologies that can be useful for government, and it's true that at the beginning, the main advantage of quantum communication was seen as being secure, inherently secure. Now, if you look at the things from a more higher level perspective, you realize that the security that quantum communication brings is solving one type of problem in secure communication system, but not all. And so there are a lot of other issues to be solved. And so it is not seen anymore as the key argument for quantum communication. Now, what is really important to us is that there are, and we have evolved from that perspective, is that actually what will be key is to make networks of quantum devices, quantum computers or quantum sensors. You see, with our computers we have on the tables, going from isolated computers to computers in a network, in the internet, has changed drastically what you can do with a computer, both on the what you can do, I mean, in terms of uses, but also in terms of processing power that you can access. And so to us, it's extremely key to prepare this kind of evolution. And this applies also to quantum sensors, because if you can build an extended coherent quantum sensor, then you will also have much higher accuracy, much higher availability. And I mean, all the key performance parameters that you would like for a sensor available and
increased. And so for us, the great goal is really to build networks that will connect these devices. And to do so,
you need to be able to distribute entanglement across the network.
Entanglement becomes the resource of the network. You have to distribute. And so we have to work on that. Of course, it's extremely challenging, and so it takes time. And so we need the first reason why we went to that is that
We have to start now if we want to be ready in 10 years' time. That's the idea. And second, the second reason, and why especially in space we are on quantum communications, is that you can do quantum communication in optical fiber, just what you use to connect your box at home, but it never goes far because fiber absorbs, while free space communication is much more efficient in the sense that the absorption is much lower. And this makes satellites basically unavoidable, unescapable in quantum communications. And so it's clearly a topic that we, as a telecom infrastructure provider, Thales Space, we are definitely interested in.
Okay, thank you, Matthias. So Jesper, before switching to the second question, do you want to add anything more compared to what Matthias just said?
I fully agree, let's say, to also the points Matthias was making. I think that's from our perspective, I mean, the very initial, we have also started very early actually to look in quantum communication, and also driven a bit by this cryptography aspect. And this was coming from the fact that we have vehicles, and our vehicles, for them, the connectivity is really crucial. So there was the initial idea, okay, how can we make sure in the future, with all the computational power from a quantum computer, which provides a potential threat to our encryption, how can we make sure that these vehicles are still securely connected? But in the end, it turns, to be more concrete, it turns out that, I mean, Airbus is also, like Thales, we are in providing infrastructure means. We are providing, for example, for institutional or for governments, end-to-end communication solutions. And we are also active in the satellite business. And here, it's exactly what was said by Matthias, that you need to make sure that if you want to go from a local level, you're just connecting maybe, let's say, two sites which are close to each other together, you want to go to a global network, you need satellites. And I think that's very important to understand that this is really a great opportunity to improve or to have this new type of infrastructure which we all expect, quantum networks. And to conclude on this, I think it's the essential goal to have it, because otherwise we will not be able to exploit the full power of quantum technologies overall.
Okay, so as you just said, so the road towards the large-scale quantum network will be very long and very challenging. So for you, Jesper, what will be the first milestone to achieve, and when do you think this will happen?
Well, I think we have already achieved quite some milestones. So the progress is impressive. It's really impressive. And there's something I think we always have to remind ourselves that if you compare a few years ago, in particular, how much has been happening in Europe is amazing. So I think we have, with the Europe QCI as a global frame on the European level, in the European Union, advanced significantly on, let's say, creating those networks. First on the national level, we have projects basically on the national level, and also now on the European level, where we could try to combine these different communication infrastructure, which are built more on a prototype level. But I mean, this is the first step. What for me would be, and this is maybe also a bit my personal belief, I think what's really important is to see also what has been done in China. They have managed to install a QKD network where you have a terrestrial network combined with a space-based network. And this is really key in the end for future quantum networks. So for me, the next step would be that we manage to install, let's say, an early operational system with maybe limited capabilities, but with scalability, where we combine terrestrial and space functions to have the short range as well as the long-range quantum communication network. And there's a chance to do this first on the cryptography side only. I mean, we will see if this how this goes, but this would be, I think, a real technology boost to have this capability and to show, let's say, first operational capabilities. And once we have, and this is something maybe, I mean, I think from a technical perspective, this is something we could do within this decade, if, of course, the budgets are foreseen. This is going to be pushed by institutions, by governments, etc. And but then the next step would be to go towards entanglement distribution. And this is probably a goal much further out, because in the end, I think also from the use case perspective, we have to understand you need, you will need a reasonable sized quantum computer first to do that, right?
Okay, so thank you. So Matthias, who do you think would be the first users of such quantum communication technologies? And do you have any use cases in mind that you are targeting?
I wanted to add some point to what Jasper said. Actually, for us, the next step is to demonstrate that we can distribute entanglement from space, because entanglement is the resource to connect quantum devices, and this is the next step. And actually, we are working on that. We are leading a consortium in France with a number of SMEs, startups, and Airbus as a supplier too, where we are actually going towards this demonstration. And so I would like to say that this is the first step, the next step, and then secure communication will be a sub-product of that. So to answer your question, who do I think will be the first users? So I think the first users will really be the people who need to exchange quantum information across networks. And this, I mean, using quantum information can be, for instance, a guy in a pharmaceutical lab that wants to test the properties of a certain molecule he has thought of, and doesn't actually have the possibility to operate its own quantum computer, so needs to connect to a quantum processing farms, so the next generation of HPC farms where you will have quantum computers, and there to be able to transfer the information, the quantum information that he has in mind to assess the properties of the molecule to the quantum processors, and then have the quantum processor execute the algorithms, the quantum algorithm there, and then send that back again through the network to the quantum terminal in the pharmaceutical company, and then exploit the measurements of the states that he will have received. So basically, the idea is that this kind of users will be probably the first ones. Also, there are also, I mean, I've been talking, for instance, with Jay Gambetta in IBM, and he told me, of course, we will need quantum information network very soon, because our computers are cryogenic. They need to be put in a fridge, and in a fridge you will never put more than 1,000 qubits, because there are so many losses after that you will need to put several fridges in the network. And this, the ability to be large-scale computers will require this kind of networks. Even at in the first place, in the same building, just to connect different fridges, and then once you have connected different fridges in the same building, it will be not such a big step to connect across different buildings and then different cities. So that's what we are working on, and that's why we are working on. And then the security aspect will come later, when we have this kind of network that are operational, because one kind of device that you will be able to connect are secure communication devices, but they will need end-to-end connections so as to be useful.
Okay, thanks. So maybe another question. So Jasper, what do you think is the hardest challenge that you will have to face or are already facing currently?
Maybe you can just add one point to what Matthias was saying, because I think one thing is for the first users, I think it's really important that you point out these commercial potential applications that which are on a local level if you want to just scale up your quantum computer, right? So this is the development which will run in parallel, but this is let's say a local quantum network. And when we talk about this, but for me this would be like really an intermediate step. In the end, we really want to be able to network globally quantum devices, and I think here that's really a big goal. If you talk more about the security, I think it's fair to say that so far this is more driven by governments and authorities. So of course there are commercial use cases. Of course you can ask a bank, and the bank will be very happy to use this type of service. But since quantum cryptography will be more expensive, it's not very hard to predict the market here. So I think it's something, once we have a network available where we can do cryptography, where we to potentially also networking of entanglement, we can have more and more users coming in. But I think the starting point on this side is more on the government side, and it's really important also that governments support us to make this happen. It's not gonna be easy from a purely commercial perspective. And then now coming to your question, because that's actually one of the challenges. So we are in this large quantum ecosystem where we have hundreds of startups developing quantum computers. We have startups focusing on local quantum networks for scaling up, and we have billions of investments. I think so far it accumulates to more than $40 billion in the quantum realm. A lot in quantum computing, and indirectly also a lot will come to quantum networks when we want to network these quantum computers. So what we have to do, and this is a big challenge, we have to make sure that we steer this exciting and emerging ecosystem in a very efficient way. So what does this mean? This means we have today in every larger country a national quantum plan where there are many, let's say, initiatives on a national or even on a local scale. We have the European level, which is very important for us, where these activities are combined. But in the end, we have also different ecosystems. You have an ecosystem in North America, you have the ecosystems in APAC. And in my view, we have to make sure that we bring all of these initiatives at least under a harmonized level to come closer to realization. So it would be a pity if we are, let's say, lost in activities and silos. We are redoing everything, and I think this is something where companies like Airbus, like Thales, who have a global footprint, can contribute to bring these various players together.
Yeah, so here you are stressing the importance of collaborations. Okay. Okay, so just we have 2 minutes left. So maybe as a last question, so if there are like any companies and people attending the seminar wants to join the global effort toward the quantum communication network, so which advice can you give them? So maybe Matthias?
So maybe the important thing you need to know is that these networks are quantum, but there are a lot of non-quantum things around, and that are completely needed for them to work. So there are things like synchronization systems, like polarization, so classical optical systems, and and on top of that, you have simple mechanical aspects of a satellite, simple power aspects of the satellites, these kind of things that are definitely needed so as to implement these functions. So I would like to tell people who would like to join that I mean it's definitely useful to have a broad vision of what a quantum communication system is, but it's also very interesting for them to look at what part of the quantum, if they have resource for that, or non-quantum if they don't have quantum resources for that, part of the system they could contribute to. I mean, and we are definitely looking for people who are willing to contribute to this kind of activities. And then on top of that, there is one key element that I try to advertise every time I have the opportunity, that there is one key element for the operational quantum communication networks that will be needed. It's quantum memories. So it's not exactly the quantum RAM that was mentioned in the quantum computation sector, but it's close to it. And quantum memories, I mean, means something in a device in which you can store a quantum state for a long time. And this we need companies that develop this, because it will be really an enabler for quantum information network. So in particular, an actor on this. So we have WILLING already. There are also actors in Spain and in the Netherlands, but definitely we need to have to progress on this side.
Okay, thank you. So maybe Jesper, a quick answer to this question before we switch to the question that the audience might have.
I mean, I can make it. I mean, I can just give maybe one statement to complement here. I think it's really an exciting opportunity, because it's going to change a lot once we have these networks in place. And so I would advise, don't wait until this is, let's say, set up and ready, But it's really, I think, a good time to start now, because we have the basics are there. We know we can basically do it. It's just now to make it happen. And the earlier you get involved, for example, as an end user, you can also shape it, right? So it's not only to provide, let's say, a component, but it's also overall to shape how this network is set up. So maybe it's really a great opportunity, and just don't wait.
Okay, thank you. So I think the message was clear. So thank you a lot, Jasper and Matthias. So I think, Corentin, we can switch to questions if you have any questions in the chat.
There's one question in the chat which we can answer very quickly. So Jasper or Matthias, between the three, quantum computing, sensor, and communication, which will be the major game changer for companies, the one which we absolutely cannot ignore? If you have an answer to this,
I can give a quick. Actually, it's difficult to separate because they will come more or less with one another. Of course, you can think of a self-standing quantum computer or a self-standing quantum sensor, but very quickly you need to connect them. So you will need the three of them, at least two out of the three.
Yeah, I would agree to the statement, particularly when you come from the perspective aerospace, because this is really, in aerospace, it's a beautiful playground for various applications in all the three quantum pillars, computing, communication, and sensing. I would say if you leave the aerospace sector and you really think from an industrial impact, at least what all the predictions are saying is that quantum computing is very early, and there are significant hurdles to overcome. But once we have a fault-tolerant quantum computer, it's going to be very impactful for many, many sectors. So that's why I think we really have to look specifically from your perspective, where are your challenges, where are your needs, and then I think it's pretty straightforward to find the answer also where to engage first.
So thank you to the three of you. So we will stop here to leave some time for Jean-Christophe conclusion, if that's okay with you. So Jean-Christophe, you can make 1 or 2 minute conclusion.
Thank you, Corentin. So it's time to try to give a synthesis. So the emergence of quantum computers promises to revolutionize simulation and optimization with huge computing speeds and lower energy consumption. Nevertheless, major challenges lie in front of us, such as scaling up and developing high-level libraries to tackle different business problems. Not all application domains have the same time scales, and it seems that quantum computing should be considered today as a pre-computational stage of classical HPC computing. Big data does not seem compatible with quantum for the moment, but machine learning seems to have reached maturity. Concerning sensor, a technical revolution is also underway in the field of quantum sensors. These offer numerous advantages: greater precision and sensitivity, so small size for a Rydberg antenna, for example, and above all, self-calibration for most atomic sensors. As we can see, there isn't just one type of sensor, but a multitude with varying degrees of maturity and different applications. We can expect the first sensors to be operationally available within the next decade. A number of applications are of particular interest: atomic accelerometers for satellite observation, Rydberg atoms for electromagnetic field sensing, and inertial sensor for global navigation satellite system. Concerning the last part on communication, the emergence of quantum technology is coupled by the development of quantum communication, of course, with two major issues at the top of the agenda: secure communication and the transfer of quantum information from one place to another. One thing is already clear: in order to deploy a long-distance quantum telecom network interconnecting computers, ground station, and mobile objects, we need to go through space. The loss is too great at terrestrial level. Research and development in quantum communication is supported by a well-structured ecosystem at European level. with concrete objective over time. For example, Europe is expected to demonstrate a quantum link via satellite. Okay.
Thank you, Jean-Christophe. So we are 1 minute late, so just conclude. So thank you to our speakers for coming here and telling us what will be the next steps of quantum technologies and what still needs to be done. I'd also like to thank our partners, EDF, Occitania, and ADOC, and the Fairfax for the co-organization. I'd like to thank Jennifer here at Aerospace Valley, which took care of the technical part of this webinar. And I'd like to thank you for attending. So with this, I say goodbye to you and have a nice day and a nice week. Goodbye.
Bye.
Thank you to all of you.